Welcome to this scientific lecture on the theory of inventive problem solving, known as TRIZ, and why its founder, Genrich Altshuller, rejected the methods used by two of history's greatest inventors, Thomas Edison and Nikola Tesla. Let's begin by understanding who Genrich Altshuller was. Born in 1926 in the Soviet Union, Altshuller was a prolific inventor who held over 70 patents by his early 20s. What made Altshuller unique was his scientific approach. He analyzed over 200,000 patents from various fields, searching for patterns in how inventors solve problems. From this massive analysis, he discovered that there are only about 40 fundamental inventive principles that repeatedly appear across different fields of engineering and science. This led him to develop TRIZ in 1946, a systematic methodology for innovation. The key insight was that invention doesn't have to be random or rely on genius flashes of inspiration. Now let's examine Thomas Edison's approach to invention. Edison is famous for saying that genius is 1% inspiration and 99% perspiration. Edison's method was exhaustive experimentation. He would systematically try thousands of materials and configurations until something worked. His most famous example is the search for the right filament material for the incandescent light bulb. Edison tested over 6,000 different materials. He tried carbonized bamboo, platinum, various metals, and countless organic materials. Each test was methodical, but the approach was fundamentally trial and error. Think about the efficiency here. If he tested 6,000 materials and found one that worked, his success rate was about 0.017% per trial. This raises an important question. Was this an efficient use of resources? Could a more systematic approach have reduced the number of trials needed? Altshuller strongly criticized Edison's trial and error method. Let me explain his reasoning from a scientific perspective. First, trial and error lacks transferable knowledge. When Edison found that carbonized bamboo worked for light bulb filaments, that specific knowledge didn't help him solve other problems. Second, it's extremely resource-intensive and time-consuming. Edison had the luxury of a well-funded laboratory and a large team, but most inventors don't have these resources. Third, and most importantly to Altshuller, it relies more on luck and persistence than on deep understanding of the underlying principles. Edison's method is like searching randomly in a vast solution space, while TRIZ provides a systematic map of that space based on patterns from successful inventions. Now let's turn to Nikola Tesla, whose approach was completely different from Edison's. Tesla relied heavily on visualization and mental experimentation. Tesla claimed that he could design entire machines in his mind, run them mentally for weeks, and then disassemble them to check for wear, all without building a physical prototype. Tesla's method was to perfect a design completely in his imagination before ever building a physical prototype. He had an extraordinary ability to visualize complex electromagnetic fields and mechanical systems. This approach led to remarkable innovations. Tesla developed the alternating current system, the Tesla coil, wireless transmission concepts, and many other groundbreaking technologies. However, Altshuller identified serious problems with Tesla's visualization method, despite its apparent success. Altschuller's critique of Tesla's method is particularly interesting because it reveals the limitations of relying on individual genius. First, Tesla's method requires exceptional, almost superhuman mental capabilities. Tesla himself acknowledged his unusual ability to visualize with photographic clarity. This makes the method non-reproducible. Most engineers and inventors don't have Tesla's extraordinary visualization abilities. So while it worked for him, it cannot be taught or scaled. Second, there are no systematic procedures or guidelines. How do you teach someone to visualize like Tesla? Where do you start? What principles do you follow? Tesla's method essentially requires genius, which by definition is rare and cannot be systematically developed in most people. Third, mental models can contain hidden assumptions and biases. Even Tesla made mistakes. His opposition to quantum theory and some of his later ideas about wireless power transmission were not practically feasible. This brings us to a fundamental question that Altshuller grappled with. Can genius be systematized? Can we take the insights of the greatest inventors and make them accessible to everyone? Altshuller believed yes. but not by copying their methods. Instead, he proposed studying the patterns in what successful inventors created, not how they personally thought about problems. So what did Altshuller propose as an alternative? Let's explore the core principles of TRIZ and why he believed it was superior. The first principle of TRIZ is that most problems you encounter have already been solved somewhere, in some form, in some field. You don't need to reinvent the wheel. TRIZ teaches you to look for solutions in other fields. A mechanical problem might have been solved in electrical engineering. A chemical problem might have an analogy in biology. The second principle is that technological systems evolve according to predictable patterns. This is called the laws of technical system evolution. For example, systems tend to evolve from monosystems to bisystems to polysystems and eventually to dynamization. Think about how wheels evolved from solid to spoke to pneumatic to adaptive suspension. The third principle is that at the heart of difficult problems are contradictions. Something needs to be both large and small, both strong and flexible, both cheap and high quality. Let me give you a concrete example. Consider aircraft design. You want the aircraft to be strong enough to withstand aerodynamic forces, but you also want it to be lightweight to save fuel. This is a physical contradiction. The structure needs to be both heavy and light at the same time. How do you resolve this? Edison would try many different materials and configurations through trial and error, testing each one until finding something adequate. Tesla might visualize an ideal structure in his mind, perhaps imagining novel geometries or material arrangements based on his intuition. TRIZ approaches this systematically using separation principles. One principle is separation in space. Make some parts strong and heavy, other parts light and thin. This principle directly leads you to solutions like honeycomb structures, which are strong where needed but use minimal material. This wasn't discovered by accident, but by applying systematic principles. The honeycomb structure is a perfect example of applying TRIZ principles. It resolves the contradiction through spatial separation of properties. Let me introduce you to some of the 40 inventive principles that Altshuller discovered. These are patterns that appear again and again in successful inventions across all fields. Principle 1 is segmentation. Divide an object into independent parts. Make it sectional for easy assembly and disassembly. Think of modular furniture or sectional sofas. Principle 2 is extraction. Extract the disturbing part or property from an object. For example, noise-canceling headphones extract unwanted sound frequencies. Principle 10 is preliminary action. Perform required changes to an object in advance. Pre-stressed concrete is a perfect example, where tension is applied before the concrete experiences load. Principle 15 is dynamics. Make an object or environment automatically adjust for optimal performance. Adaptive cruise control in cars is a modern application. Principle 35 is parameter changes. Change the physical state of a system. Freezing water to make ice for cooling is a simple but powerful example. Now let me share some real-world examples where TRIZ dramatically outperformed trial and error approaches. These examples validate Altschuller's critique. In the 1990s, Procter & Gamble faced a problem with disposable diapers. The adhesive tabs would stick to the diaper and tear it when the package was opened. A trial and error approach would test hundreds of different adhesive formulations, varying tackiness, chemistry, and application methods. This could take months or years. TRIZ identified this as a standard problem of harmful interaction between two components. One of the 40 principles is intermediary. Insert an intermediate object between two components. The solution was to insert a release paper between the tab and the diaper during manufacturing. This simple solution was identified in days using TRIZ principles. A semiconductor company needed to detect microcracks in silicon wafers. Traditional optical inspection methods couldn't detect them early enough. Trial and error would involve testing different wavelengths of light, various imaging algorithms, electron microscopy, X-ray methods, and so on. Very expensive and time-consuming. TRIZ Principle 13 is the other way around. Invert the action or make the movable part fixed and the fixed part movable. Combined with field analysis, engineers realized they could heat the wafer slightly. Microcracks would expand at different rates than solid silicon when heated, making them easily detectable with infrared cameras. Problem solved in weeks instead of months. Now we arrive at the critical question. Was Altshuller right in his critique of Edison's trial and error method? Let me present both sides of this debate. First, let's look at arguments supporting Altshuller. From a resource efficiency standpoint, TRIZ is clearly superior. Studies show TRIZ can reduce problem-solving time by 50 to 90%. Modern corporations like Samsung, Siemens, and Boeing use TRIZ precisely because it saves time and money compared to pure trial and error approaches. Second, TRIZ enables knowledge transfer. When you learn the 40 principles, you can apply them to any field. Edison's filament knowledge didn't help with batteries or phonographs. Third, TRIZ democratizes innovation. You don't need Edison's resources or Tesla's genius. An average engineer with TRIZ training can solve problems that would stump untrained experts. However, there are also legitimate arguments defending Edison's approach. First, Edison worked in an era before systematic innovation theory existed. Second, trial and error builds deep empirical knowledge. By testing 6,000 materials, Edison learned countless properties that informed his later inventions. Third, some problems genuinely require empirical data. TRIZ can suggest that you should try high melting point materials for a filament, but it can't tell you the exact burn rate of carbonized bamboo versus tungsten. Fourth, Edison's method led to unexpected discoveries. While testing filaments, he discovered thermionic emission, which later enabled vacuum tube technology. Systematic approaches might miss these serendipitous findings. The truth is that modern innovation often uses a hybrid approach. Use TRIZ to rapidly narrow the solution space, then use empirical testing to validate and optimize. Now let's address whether Altshuller was right about Tesla's visualization method. This is perhaps more controversial than the Edison critique. Supporting Altshuller-Tesla's method is fundamentally non-transferable. You cannot teach someone to visualize at Tesla's level. This is a scientific fact about human cognitive variation. Neuroscience research confirms that visualization abilities vary enormously between individuals. Some people have aphantasia and cannot visualize at all. Studies suggest fewer than 10% of the population has visualization abilities approaching Tesla's level. This makes it unsuitable as a general methodology. Moreover, Tesla himself struggled to document and explain his methods. Many of his later ideas remained unrealized because they existed only in his mind. However, defending Tesla visualization is an incredibly powerful tool when combined with deep domain knowledge. Modern computational simulation is essentially mechanized visualization. Computer-aided design, finite element analysis, and virtual prototyping are tools that extend Tesla's visualization approach to engineers who lack his natural ability. In this sense, modern technology has vindicated Tesla's approach while addressing Altschuller's critique. We can now give everyone Tesla-like visualization capabilities through software. Furthermore, deep intuitive insight can actually accelerate TRIZ application. The best TRIZ practitioners combine systematic methods with strong visualization and intuition. This debate touches on a deeper scientific question about the nature of innovation and problem solving. Is innovation primarily a matter of method or capability? Altshuller represents the view that innovation is primarily methodological. It's a learnable skill that can be taught through systematic principles and procedures. Edison and Tesla represent different aspects of the capability view. Edison showed that persistence and resources matter. Tesla showed that exceptional mental abilities matter. Modern cognitive science and innovation research suggest both are important. There are individual differences in creative ability, but systematic methods dramatically improve outcomes. We might model it as innovation equals method times capability times domain knowledge. All three factors matter, and they multiply rather than add. Let's look at evidence from modern studies of innovation and problem solving. This helps us evaluate Altschuller's critiques more objectively. A 2015 study by Ilevbeer, Probert, and Fall found that TRIZ reduces average time to solution by 60% compared to unstructured brainstorming and trial and error. The same study found that solution quality, measured by novelty and effectiveness, improved by about 40% when using TRIZ principles. A 2018 study found that hybrid methods combining TRIZ with empirical testing and computational simulation outperformed any single approach by significant margins. Success rates for solving novel engineering problems were 67% for TRIZ-trained teams versus 23% for teams using only trial and error methods. However, we must also acknowledge the limitations of TRIZ. No method is perfect, and understanding these limitations is crucial for scientific objectivity. First, TRIZ has a steep learning curve. Mastering the 40 principles, contradiction matrix, and standard solutions requires months of training and practice. Second, TRIZ was developed primarily for technical and engineering problems. Its application to social, organizational, or artistic problems is less clear-cut. Third, TRIZ might constrain thinking to known patterns. If a problem requires a genuinely new principle beyond the 40, TRIZ might not help and could even create mental rigidity. Fourth, some radical innovations historically came from accidental discoveries during trial and error. Penicillin, the microwave oven, and Post-it notes were serendipitous discoveries. So what's the synthesis? How should we view Altschuller's critiques in light of modern evidence and theory? Let me present a balanced, modern perspective. First, Altshuller was substantially correct about efficiency. For most problems, systematic methods outperform pure trial and error by wide margins in terms of time and resources. However, Edison's empiricism remains necessary. TRIZ suggests directions but cannot replace experimental validation. You still need to test your ideas against reality. Regarding Tesla, Altshuller was correct about non-transferability. You cannot teach Tesla's visualization ability, making it unsuitable as a general method. Yet modern computational tools have essentially democratized Tesla's approach. Computer simulation gives ordinary engineers visualization superpowers. The modern innovation pipeline integrates all approaches. Use TRIZ for rapid solution generation, simulation for virtual validation, testing for empirical confirmation, and iteration to optimize. The optimal approach depends on context. For well-defined technical problems, TRIZ dominates. For exploratory research with unknown parameters, trial and error may be necessary. What are the practical implications for modern innovators and problem solvers? How should you approach innovation in light of this analysis? First, learn TRIZ as a foundational skill. Even basic familiarity with the 40 principles will make you a more effective problem solver across any domain. Second, develop deep domain expertise and empirical skills. TRIZ is most powerful when wielded by someone who deeply understands their field. Third, leverage computational tools. Learn CAD, simulation software, and data visualization. These tools amplify your mental models like a telescope amplifies your eyes. Fourth, never abandon empirical testing. The universe is more complex than any model. Reality is the ultimate arbiter of whether solutions work. Fifth, cultivate both systematic and intuitive approaches. Use TRIZ to generate candidates, but also trust your intuition to recognize promising directions. Let's conclude with some historical perspective and thoughts about future directions in innovation methodology. TRIZ itself has evolved considerably since Altschuller's original formulation. Modern TRIZ incorporates computational methods, machine learning, and systems thinking. Artificial intelligence and machine learning are beginning to transform innovation methodology. I can now search patent databases and suggest analogous solutions automatically. Generative design algorithms can explore millions of design variations and optimize for multiple objectives simultaneously, something impossible for human designers. The future likely involves integration of TRIZ principles, artificial intelligence, and advanced simulation into unified innovation platforms. However, human insight, intuition, and creativity remain irreplaceable. Algorithms can suggest solutions, but humans must evaluate their appropriateness and elegance. So was Genrich Altshuller right to reject Edison's trial and error and Tesla's visualization as general methods for innovation? Let me give you my scientific assessment. Altshuller was fundamentally right about the need for systematic innovation methods. The evidence overwhelmingly supports that systematic approaches outperform unstructured ones. He was right that innovation should be democratized and teachable. TRIZ has enabled countless engineers to solve problems they couldn't have solved otherwise. However, Altshuller was perhaps too dismissive of the value of empiricism and intuition. These remain essential components of the innovation process. The methods are complementary, not contradictory. The best innovators combine systematic principles with empirical validation and cultivated intuition. Think of it as a Venn diagram. The sweet spot is where systematic methods, empirical testing, and intuitive insight overlap. That's where the most powerful innovation happens. Let me summarize the key takeaways from this scientific analysis of TRIZ versus historical innovation methods. First, systematic methods like TRIZ dramatically improve innovation efficiency for most technical problems by factors of 2 to 10. Second, pure trial and error is wasteful but not worthless. It builds empirical knowledge and can lead to serendipitous discoveries. Third, genius-level intuition like Tesla's is powerful but fundamentally non-transferable without technological aids. Fourth, modern computational tools enable hybrid approaches that combine the strengths of all methods while mitigating their weaknesses. Fifth, context determines optimal strategy. Well-defined problems favor systematic methods. Exploratory research may require more empirical approaches. In conclusion, Genrich Altshuller made profound contributions to innovation science by systematizing what had previously been treated as magical or mysterious. His critiques of Edison and Tesla contained important truths about the limitations of unstructured trial and error and non-transferable genius. However, innovation is multifaceted. No single method captures all aspects of creative problem-solving. The future belongs to integrative approaches that combine systematic principles, computational tools, empirical validation, and human creativity. Learn from all the masters. Study TRIZ for systematic thinking, appreciate Edison's persistence and empiricism, and cultivate Tesla's ability to deeply visualize and understand systems. I'll leave you with a question for reflection. Given your own cognitive style and the problems you work on, which approach resonates most with you? And how might you integrate insights from all three? Thank you for your attention to this scientific analysis. I hope this lecture has given you a deeper appreciation for the nature of innovation and the ongoing evolution of innovation methodologies.